So, hi everybody, and welcome to the 12th lecture of wireless communication course. In today's lecture, we will be talking about adaptive modulation. In the previous lecture, we talked about diversity concept and the techniques that are used at the transmitter and receiver to avoid or reduce the effect of fading on your overall performance. So, diversity is basically a technique that used in wireless communication system to mitigate the effect of fading on your performance. So what other techniques we can use in order to deal with the fading or to deal with the impairments of wireless communication channel? A technique that can be used is adaptive modulation. Now, before adaptive modulation, everybody must know what's modulation, and we explained it in the previous lecture. What's modulation? Mapping the bits into the features of your sinusoidal carrier, including the amplitude, phase, or frequency, and it can be hybrid as well. So, in the outline is going to be structured as follows. First, we'll introduce you to the basic concept and basic definition of adaptive modulation. Then we discussed how to perform variable rate, variable power allocation, and then optimal power and rate adaptation according to the channel quality and according to the requirements of the application you are trying to serve. And then we discussed the finite constellation sets in modulation schemes that you select among them. So adaptive modulation, the simplest definition for it is changing the modulation relative to the channel quality and to the application requirements. So adaptation means adjust, modify the things, make them cognitive, not always fixed. So this is a technique that actually used to provide link adaptation. There are many techniques for link adaptation, like power optimization, ARQ, automatic repeat request, modulation, coding, spreading, interleaving depth. All these are physical parameters that you can adapt based on your quality of your channel and the requirements of your service or the application you are trying to serve. So what are the parameters that you can adapt or change? The constellation size of your modulation scheme. For example, 16 EQAM has 16 symbols in the constellation diagram, or 16 messages. You can also you can adapt and change the transmit power according to your needs, the bit error rate target, the symbol time, which also affects the symbol bandwidth, the coding rate, the number of retransmission, the spreading code, the interleaving vectors. All these are parameters that you can change and adapt according to the situation of the channel. So basically the goal here to maximize your throughput, your data rate, or minimize the average power, or minimize the bit error rate, or maximize the secrecy performance of your system. And this can be with conditions and it can be conditionless. Means you are okay with whatever you do, no matter what complexity you use, no matter what delay you cause, no matter what power you use. The most important thing to you to adapt your communication design in such a way that you provide the highest throughput possible. So this is strategy just to make you understand things, but in practice we always have some limitation on the complexity, on the power consumption, on the delay, on many parameters. So in practical optimization techniques and adaptation methodologies, we have to consider all the effect of all these other parameters because they affect the overall performance of the system. So in general, there is a thumb rule that we need to follow in order to get good performance for your system. You need to change at least 2 degrees of freedom needed for obtaining good performance. So you change 2 of these, or sometimes 3. It depends. The more you make your system flexible, the more gain you can get. So this is the basic definition of adaptive modulation. Now we said one of the parameters you can adopt is the constellation diagram. These are examples of different modulation schemes that we have to look at them so that you understand the whole picture of adaptation regarding modulation. So we have 4 equam, which is quadrature amplitude modulation, a modulation scheme that you change the amplitude and phase simultaneously, 16 equam, and 64 equam. So as you can see, as this number before equam increases, as the number of points, which represents actually the number of points inside the constellation. The constellation diagram gets larger. And as you can notice, when you increase the modulation order, this we call it M. This M equal here 4 or 16 or 64. When M is small, the distance between the symbols is large compared to large M. Yes? What does this mean? If the distance between the symbols in the constellation diagram is small, what does this mean? It's more prone to errors, susceptible to noise errors. For example, if you have noise here and the noise pushed your symbol here, the receiver will decide wrongly on this symbol. Yes? While here you have more degree of freedom. This is the decision boundaries, and you want to make sure that each symbol was received within its region. If it crosses the region, you will make an error. So what can you conclude from here? That the modulation order affects the distance between the symbols, and that's why it affects the bit error rate. Automatic. This intuitive. Yes? What else you can consider? When you increase the modulation order, what did we say about modulation? We said when you increase the modulation order, like to high values, you can encode more data bits to each symbol. For example, each symbol here carrying how many bits? The symbol here in 4 equam. You have 4 different possible values. How many bits each value can carry? 2 to power how much equal 4? 2. So each symbol here is representing 2 bits. Because modulation, you have the bits coming here in data stream. Yes? And for 4 equam, since you have 4 levels, you can put in each level 2. While in 16, 4 bits. While 64, 6 bits. Each symbol carrying 6 bits. So which one is more spectrally efficient? 6 bits, the one that sends 6 bits per symbol. More spectrally efficient. But makes more error. So there is a trade-off. You increase your spectral efficiency, but you lose in the bit error rate. Now, not only this is the modulation order, but also you can change for one specific modulation scheme, like 16 equam, you can change the constellation shape. For example, this is rectangle. See how the values are placed in the constellation diagram? While here, they are placed, for example, here we have 3 different amplitudes, 12 different phases. Where are the different amplitudes? This is one with respect to the origin. This is first amplitude, this is second amplitude, which is the same as this, and this is the third amplitude. 3 different amplitudes. Whereas here we have 4 different amplitudes. Here we have 2 different amplitudes and change number of phases. Now, different constellation diagrams have different performance. You must know this because the way you place them in the constellation affects the overall performance. Not the spectral efficiency performance, maybe, because all of them, they have the same number of values you can place, 16, 16, 16, so the spectral efficiency is the same. But bit error rate is not the same for all of them. That are the things that I want you to know about modulations. Now, draw the bit error rate of these different modulation Constellation over an additive white Gaussian noise channel or fading channel. This is the y-axis is the bit error rate. The x-axis is the signal to noise ratio. Signal to noise ratio, we said it's the power over what? Over noise. We call it sigma square or N naught. So the bit error rate, the binary phase shift keying performance is shown in this curve, which is the purple one. Then you have the QPSK performance. Actually, when you consider the same data rate, same power, both of them, they should be exactly the same. But this is for the case when you are saving power in QPSK. You get this. And for 16 QAM, you get this bit error rate, and for 64. What do you notice here? As the modulation order increases, the bit error rate performs worse. Yes? For example, if I tell you which one has the best bit error rate performance, BBSK, first one, worse, 64 QAM. Now, what's the difference between each two one? Is also something that we can look at it. Now this is the bit error rate. Now on the other hand, there is the spectral efficiency, which is how many bits you can transmit per symbol per hertz. For example, in BBSK, what's the maximum number of bits you can transmit? You have only two values in the constellation diagram, 2 to the power how much equal to 1. Only 1 bit per symbol. Where QPSK, you only have 2 bits per symbol. 16 QAM, you have 4 bits per symbol. 64 QAM, you have 6 bits per symbol. And this is the spectral efficiency. Now we know this is the maximum you can achieve, but it changes as function of the signal to noise ratio. Now you tell me I have all these different values, but as we know, the signal to noise ratio in the channel is not always 15 or it's not always 30. So you must adopt. This signal to noise ratio is the average signal to noise ratio. Suppose there is a base station here and the user is here near to the base station. What's the signal to noise ratio here? The signal to noise ratio is high, like let's say 40. If it is 40, which modulation scheme you can use? 64, because the signal to noise ratio is high, I can still give the user high order modulation while still getting good bit error rate. See, at 30, you have 10 to minus 10, which is very nice bit error rate. But I can't use 64 at 10 dB. When the user moves away from the tower and goes, let's say, 2 kilometers away on the edge of the cell, what's the signal to noise ratio? The signal to noise ratio decreases to, for example, 15 or 10. Now for 15 or 10, let's say 15. What's the bit error rate of 64 QAM? Very bad. I'm saying the bit error rate depends on the application. Let's say he's using video. Video requires something like less than 10 to minus 4. Can he use 64 QAM when he's on the edge, when he's very far from the tower? He cannot. Can he use this? He cannot, because if he chooses to use this, he will not be able to decode the data of the video. Yes? So what he has to use is this QPSK. Similarly, you can apply this to this is just how to adopt the modulation with respect to the signal to noise ratio, which represents the distance average. Now also you can adopt your modulation with respect to fading, because we said that modulation is a technique that can adapt to fading, not only to the average signal to noise ratio. True, how do you do that? Suppose the user is on a fixed distance from the base station, But let's say this is the base station, and there is one user here, one user here, and one user here. All of them, they have the same distance. So obviously, you must use the same modulation for all of them because they have same shadowing, same path loss. But since they have different locations, then obviously they have what? Different channels. Yeah, and these channels, they are uncorrelated, independent. So this user over this time has good channel. What can you do? You can increase the modulation order over this. While this user has bad channel, what do? You give him low modulation order. This user is in between. What do? You give him in between modulation order. So with these two examples now, you know how to adapt your modulation according to the average signal to noise ratio and how to adapt your modulation according to channel fading of your channel. Fading of your channel when all the users are located on the same location from the base station. They have almost similar path loss, similar shadowing, and in this case we say that they have same large scale fading because large scale fading includes path loss and shadowing, where small scale fading includes fading, fading and multipath fading. So you know how it makes sense? Makes sense? Anybody, like, just let him think. He would rather, instead of using only fixed modulation for all the schemes, make it adaptive based on the scenario. What happens if you use fixed modulation for all the cases, for all the channel qualities? Tell me. Suppose you decided to use 64 equam. This guy, his channel is good. He can decode the 64 equam. But this guy, his channel is so bad. How can he decode it? Yeah, gives too much error, too many errors. Yes, he cannot decode it successfully. That's why you got the importance of adaptation. The same with adapting with respect to the large scale fading, path loss and shadowing. If this is a clause, why should I give him only BPSK? The signal to noise ratio is very nice, very good. I must increase the modulation order because he can decode higher order modulation order with low bit error rate. Nice. Give him 64 equal. But if he moves far away from me, I can no longer support this user with large order modulation. Yes, one question.
Can I give two modulations at the same time?
Two modulations for one user?
For one.
Two modulation. Why do you need to give two modulations at the same time?
Because to ensure the two conditions.
Which conditions? You can only give two different modulations for the same time. For example, suppose the base station is like suppose the user is asking two applications from the base station. Let's say one is messaging and the other is video. Now for video, the user requires high data rate, high spectral efficiency. So you must map higher order modulation to video. While for texting, you don't need high data rate, you need highly reliable. So the one that has better bit error rate, you map it to messaging. And the one that has better spectral efficiency, you map it to video. This is a scenario where you can give two modulations, but not based on the channel in this case, because the user in fixed location. Yes? So if I tell you, give me two cases where you adapt your modulation, two scenarios. You adapt based on the quality of the channel or based on the requirements of the application that the user is using or running at his mobile. True? Make sense? We have two. The channel includes fading, multipath, intersymbol, many things, many issues. And the application, we have so many applications. We have texting, file uploading, VoIP, voice, video streaming, gaming, web browsing, and all of them, they have different requirements. Yes, everybody knows, most of you guys are from computer, you know that these applications, they don't have the same. Even you take this into the consideration of designing your network layer. For example, there are applications that are delay tolerant, like for messaging, but for real-time streaming, what do you need to do for network simulator? You need to make sure that the delay is not exceeding certain limits, certain threshold for designing routing scheme and this. So it does not only relate to the physical layer, but also involves the MAC and network. But this is how we fix this problem at the physical layer. Is this the only solution, adaptive modulation? No, of course, we have also adaptive power allocation. Instead of changing your modulation, you can change your power. For example, when the user is here, I don't need too much signal to noise ratio. I can transmit with low power, but when the user is very far, you need to increase the power. Also, you can use both power and modulation, adaptive power, adaptive modulation, to adjust based on the channel conditions and application requirements. Now, with this have been said, let's now dive into the math and the formulas and the optimization things. Variable rate. Variable rate, how do you get variable rate? By changing M basically. You get different rates, different throttles, different spectral efficiency. Variable power by allocating power to your subchannels. You have in a communication system, you have your encoded data bits, which are generated from your text or video or whatever. At the end of the day, what you are transmitting is bits, yes? And then there is here, the receiver, if he's gonna use adaptive modulation, he needs to be in a waiting process here, waiting for an update from the channel. Yes? Why? Here, the transmitter suffers from some delay. He needs to wait for the receiver to send him something so that he can adapt. Can he adapt blindly? He cannot. He needs to get some information about the channel, the application, this. And to get this information, you must be patient. That's why it delays your transmission a little bit, because you need to get feedback from. The way I get feedback from you, I wait to receive a feedback and accordingly I adapt. So the same, the transmitter here waits for the receiver to send feedback about his signal to noise ratio or his fading situation or the application he's using. And then based on these parameters, like all, for example, channel, application, fading, feeds them in a number. Each number maps, the transmitter has this mapping table. If he receives this number from the receiver, this means use modulation number 1. If he receives number 2, use modulation number 3, 4. So the receiver do some processing and decides which mode suits him the best. And this is a clever mechanism of transmitting your data, isn't it? And this idea of adaptation is so amazing, so beautiful that you can apply it to any field you are in. Any field, network, computer, this basically adaptation is a subset of optimization, but adaptation, we use it in situations where you cannot find closed form solution for optimization. So it's, to me, adaptation also meets artificial intelligence in a sense, machine learning. What are the optimal things to make you able to recognize things? What are the optimal weights? What are the optimal values, the optimal delays, the optimal layers, yes? So adaptation means that thing. So adaptations means cognition, means intelligence, means being able to react according to some information you have. Yes, not only blindly sending for the worst case scenario. Different user, different requirements, different applications, different channel conditions, different tests. So these are inputs. You put them and you make some processing, this selection process and mapping and this, to match the expectations of your customer, and the customer happy, your company can make profit. If he's not happy, you are not making profit, not successful business. This is how it relates to your business. And now you select your modulation after you decide based on the signal to noise ratio. We call N, this is the modulation order, function of what? The signal to noise ratio, which represents the channel equality. And then here also you can optimize your power as a function of the signal to noise ratio and send to the receiver over the channel. Clear? This BBSK, blue with red QBSK, all of them 16 equal. Nice. Adaptive modulation equal, rate for fixed bit error rate. Here, this is used for the scenario where the user is using only one application like voice, and the voice requires only 10 to minus 2 bit error rate. So let's go to the figure here. The user is moving away from the base station. The user is moving out towards the base station, let's see. So he was very far here. Where is 10 to minus 2? This 10 to minus 2. Yes, everybody with me? This is my target, fixed bit error rate. Yes? And the user is coming. This is the base station. Let's imagine the scenario. This is the base station and this is the user. The user is moving towards the base station. When he was far from the base station, to serve his call with 10 to minus 2 bit error rate, this 10 to minus 2, I can only use BBSK. Yes? So here, when the signal to noise ratio is low, 4 dB, very far from the base station, what do you use? You use BBSK. Now, the user is moving towards the base station. While he's moving, what happens? Distance reduces from the base station and the signal to noise ratio improves. Now, when it improves, he reaches to signal to noise ratio of 8. Yes? What happens here? 8. I want only 10 to minus 2. If I am still using BBSK, I'm reaching 10 to minus 3. I don't need 10 to minus 3. This is over what I need in terms of bit error rate. So why don't I make why don't I increase the speed of my internet by increasing the data rate and moving to higher order modulation? So when you reach here, when you reach to this threshold, you keep using BBSK, and then you switch to this curve. Why? Because now I can get 10 to minus 2, which is the requirement of voice communication, while also enjoying higher speed. Higher speed because QBSK faster gives more bits per symbol. You keep moving, the user keep moving. Here, the user switched to QBSK. Yes? Here QBSK, here it was BBSK, and the user keeps moving toward the base station. At this point, where the signal to noise ratio becomes 14 or 13, I can use now 16 equal. Jumps again to 16 equal curve. Got it? This is the adaptation with respect to large scale fading. What about small scale fading? How does this happen? You want fixed bit error rate. The user is here. This is the base station. The other example. This is the base station and this is the user. At time equal t0, the user has this channel, low quality, low amplitude. So the base station has to use what? Lower order modulation to achieve 10 to minus. After 5 seconds, after 1 minute, the channel improved because the channel is time varying, yes? Changes with time. Improved. He is still in his location. The channel now improved after 5 minutes. can I still keep using the same modulation order? I will be not efficient. So I jump to higher order modulation while I'm still in the same location. So adaptation can be for moving users or static users if the channel is varying. So this is the thing. Clear? Yes, one question.
If somebody reach a point between the two curves, between the QPSK and the PSK, what's the modulation regime?
Here, exactly, yes. In this case, since here, this is rough tuning. We have fine tuning. You can achieve fine tuning by integrating coding with modulation. When you integrate coding with modulation, you get very small step size between them. So you always have one curve very close to you. But now this is rough, which is something we call it adaptive coding and modulation. So you got the idea. This is the most important thing. And this is how you change the modulation order based on the signal to noise ratio. Yes? Your bit error rate target, your signal to noise ratio, this represents what? Bit error rate application. And this represents what? The channel condition. And based on this formula, you decide what's M. And as you can see, it's function of gamma, which is the signal to noise ratio. And this is the power distribution as well. You can play with it. This is the math, but you got the concept. The math, once you get the concept, after that, the math to you makes sense. But if you don't get the concept, the math with respect to you, nonsense. You cannot read it. But now you read it, I can understand, I can see this bit error rate as the application using voice, video, streaming, VoIP, web browsing, and I can see this as path loss, shadowing, how far the user from the base station, how the signal, if the user is in a fixed location, how the channel is changing with time, what should I do? Clear? Now you can read it. You know, this is the beauty of the equations. It's so too much information in few parameters. So if you don't explain the intuition behind it and this, you cannot get ideas. You cannot visualize things and understand them coherently. So to optimize the rate and the power and rate, you maximize basically optimization, which means adaptation basically. You try to maximize the data rate here, look to M. By what? By changing the power distribution. And here the same, you substitute the value of M, which is this, we get it here. And this equation, I think you cannot find a closed form solution for it. That's why we use mapping. We use mapping table at the transmitter, mapping table at the receiver. The receiver receives the signal from the transmitter. Yes, then the receiver measures the average SNR and do some calculation, and after he does all these calculations, he finds out that the best modulation that's mapping to this signal to noise ratio is this. This modulation corresponds to number 3. Then the receiver sends back number 3 to the transmitter, tells him please use mode 3 for transmission because this is my condition, this is my situation. So the receiver keeps updating the transmitter every once in a while to make sure that both of them are utilizing their transmission efficiently. This is something that we always see sometimes. Have you ever worked on communication, a broadcasting company? Broadcasting, when they have live event, they want to broadcast over the satellite to allow audience to watch the program live on TV. Quickly they set up a satellite link, yes, and the engineer behind this software that controls the link, what does he do? Anybody knows? He just keeps changing the modulation order and this. If it's not automated, if it's not this, so the quality is bad, please reduce the modulation order. Oh, the constellation are clear, good, increase the modulation order. Oh, no, now you have these small step size, you can play with it, please change the coding rate. increase, reduce this. So it's game, really, game based on optimization, trying to get the best you can get out of your available link equality and this and that. Got it? Now, power adaptation, we already explained this in the previous lecture. We said power adaptation is a way to reduce the effect of your channel and maximize its capacity. Yes, when the channel is low, when the channel is really low quality, you need to put more power so that you can compensate for the degradation that the channel caused to your data. And this is the formula that we used, water filling, and the spectral efficiency can be calculated according to this integration, which is rate over bandwidth, integration of gamma over gamma k, where gamma k here is the threshold at which you can decode your data successfully. And this is the spectral efficiency curve for two different cases, two different scenarios. So the first scenario, this is Shannon capacity. This is the maximum you can get here. This is not something we can do anything about it. We try to be close to it usually. But for the case when you have bit error rate of 10 to minus 3, yes, 10 to minus 3, what this resembles video, for example. Yes, 10 to minus 3, I can use higher modulation order compared to 10 to minus 6. Yes, so the capacity you will get is something like this. This is the capacity adaptive MIMO-OFDM for the case when the bit error rate is 10 to minus 3. Now, if your target bit error rate reduces to 10 to minus 6, then in this case your capacity reduces to this. So what's the point here? Better bit error rate, less capacity. This is the price you pay. Yes, because you want better bit error rate at low signal to noise ratio. How can you do that? By using low order modulation. Low order modulation, the number of bits you can use per symbol, low compared to high order modulation. So this is trade-off that exists in the nature of designing wireless communication systems. I wish we can break this trade-off. Someone in the future come and say, I came up with a technique where I have no trade-off between bit error rate and the spectral efficiency. I can improve the spectral efficiency and improve the bit error rate simultaneously. This is not a possible thing in the current wireless science, in the current communication science as a whole. Now, for you to think of these great ideas, you need to break away from the design of current communication systems, because as long as you are using these modulations and these structures, you cannot escape from this trade-off. So to come up with something that can achieve good in both metric, in both performance measures, you must come up with something different, because you cannot use the same modulation schemes and say, I will not have this trade-off. Because I told you the trade-off, due to the distance between the constellation diagram. More points in the constellation diagram, they get closer to each other, the distance reduces, the bit error rate becomes worse, but the spectral efficiency is high. So when you want to achieve good in both, don't even think of these modulation schemes. You must get creative, think out of the box and think of something different. I don't know what's this, but I know now it's not available in the literature, but in the future I don't know what the future is hiding from us, but a good, intelligent researcher can find a solution for that. We don't know. Now the systems are adopting based on this limitation because of that. Now, is this possible, not possible? These are open questions, exclamation mark. But I'm just giving you directions or ideas in the future. If you find yourself in this field or in any other field, and you want to do ground shaking and breaking research where can really creating new paths and routes for the new coming researchers, you need to do something really significant, not minor. So the constellation restriction, we already discussed this verbally. By concept in this, you have the modulation order, which takes value from 0 to m, and this modulation order is function of the signal to noise ratio and the target signal to noise ratio, which represents the bit error rate. And then you try to maximize your data rate, and this is what you get. As the signal to noise ratio improves, you can select higher order modulation. This is with respect to the channel, and this actually affects the application. For example, when this changes for a different application, you get different curve. Yes. And power adaptation, you can also use it instead of modulation adaptation, or both together, because basically adapting the modulation as if you are changing the power at the end of the day, but like for different purposes actually. For the case when you want fixed bit error rate within each region, so this is your signal to noise ratio as a function of the modulation order. Channel inversion within a region. Channel inversion, already we discussed it, the water filling thing, and this requires power increase when increasing the modulation order. Yes? The average rate you get is the summation of the rate log to m multiplied by the probability of your signal to noise ratio. Basically, these formulas are just related to the general cases, all the cases that I have detailed earlier and previously. The most important thing to relate these equations to the practical scenarios and the practical applications. So, for example, this shows you the efficiency in Rayleigh fading channel. When you have a fading channel and you use adaptive power, adaptation in power and modulation. Continuous power, what continuous power means? You are allowed to use any power value. So it's continuous, not discrete. For the case when you have continuous power, continuous rate, you get maximum efficiency, but this is not practical, which is this curve. This is not practical, unfortunately. When you can change the power values and the modulation order continuously, even with the tinny, your question when you asked me there is a space between the what can I do between the curves, between the two. If you have continuous values, then you have infinity number of these curves. You can switch to any based on minimal changes in the signal to noise ratio. But what will do this to your system will complicate it, will make it extremely difficult for the receiver. The mapping table will get large, the complexity of detection increases, and many issues with the too much complex. That's why they don't use it in practice. But this can be a benchmark that you can always compare with respect to it. Continuous power discrete rate gives you this curve, the blue dots here. Discrete power and discrete rate, it's this. This is somehow practical, but depends on the number of values you are limited with. And here, for this, the yellow one, fixed rate with channel inversion, and this is not adaptive. So basically, we like to use this. This is practical. The third curve here, the purple one. This is practical, and also provides you with good performance. I know it's not the best possible performance, but within the limitation of the practicality of our system, it's fine and it's acceptable. So with this, we can conclude our lecture about adaptive modulation by stating the following points. First, adaptive modulation leverages fast fading to improve performance. Not only fast fading, as I showed you at the beginning. Large scale fading and small scale fading. Large scale fading depends on the distance and obstacles and this, and small scale fading, which is related to fast fading, and this depends on how the channel varies with time. Improves performance, and including the performance which is represented by throughput, bit error rate, power saving, and so on and so forth. Adaptive MQAM, which is the one used in practical wireless standards like LTE, 3G, 2G, 2G even Edge, you know, GPRS and Edge technology, and this, they are using these adaptive modulation schemes. And they became an inevitable part of the wireless design standards. Everybody using them, everybody depends on them, because you want your system to be efficient, not designed for the worst case scenario or the best case scenario, because your system in between will not be efficient. Uses capacity, this adaptive MQAM uses capacity achieving power and rate adaptation with power penalty. You pay some penalty in terms of power and complexity. And it improves your performance within 5 to 6 dB. Discretizing the constellation size results in negligible performance loss. When you discretize here, see the loss between these 2 points. There is loss, but it's acceptable, we say. That's why here we say it's described as negligible performance loss. Because not that much, but what we gain low complexity. Constellation cannot be updated faster than 10 seconds. So you cannot update your constellation within a period less than 10 seconds, because you need time for the message, for the update message to reach the receiver and the receiver to act. There is delay, transmission and reception. We call it round trip time. When you do, with the ones who know computer networks, and you ping for an IP, round trip time. If the packet exceeds certain delay, failure, doesn't reply, yeah. So the same here in wireless communication. We have this round trip time, forth and back. Constellation is this. Constellation diagram is this. I already explained it before I start talking about the math or anything. This is constellation diagram. How the points, the symbols are placed in the I and the Q. I phase represents the cosine sinusoidal signal, the carrier, and the Q represents the sinusoidal carrier. So by changing their properties in terms of amplitude and phase and this is a representation of how their amplitudes and phases are changing. And these are linked to database, mapped to database. Clear? This is the constellation. All our talk about M, the number of these points inside the constellation diagram. Because at the end of the day, we know the x-axis is cosine, the y-axis is sine, and what are the features of cosine and sine? The amplitude, the phase, and the frequency. QAM uses only amplitude and phase, changes the amplitude and phase based on the incoming information. So these are the things. Of course, there can be estimation errors, delay, which causes error flow. All these are parameters that we must consider them while we are designing our adaptive communication systems. So with this, we finish our lecture, and thank you for your attention, and meet you in the next lecture. Thanks.